here today talking to you about timing attacks, about timeless timing attacks. That's a work in collaboration with Matti Van Hoof and with Tom van Goethem. And I would like to first give you a short introduction to my lab and the research that we're doing. That's going to be the shortest part of it. And then we'll move on to talk more general about timing attacks and the particular timing attacks that we have considered in this work here. Okay, so let me get started. First of all, a little bit of introduction about the lab. So I'm heading the Cybersecurity and Privacy Lab at New York University in Abu Dhabi. Our focus is in general about communication security and communication privacy. Our work there is based on 3 pillars. The first pillar is on mobile and cellular network security. And we have focused in the past in particular on LTE communication. We're increasingly focusing on 5G, and we're investigating the security of the systems and trying to attack and see where we can, basically where our attacks can lead to improvements in the specifications or in implementations of devices. The second pillar for us is secure localization and aviation. These are questions about GPS security, detection of GPS spoofing attacks, ADSB security as well. That's a protocol used between aircraft. Coordinating the communication and control between aircraft, and there we are also investigating the security of these systems that are inherently less secured than our mobile and cellular networks. And the third pillar of our research is on network anonymity privacy in a broad sense. So there are works on Tor and anonymity networks, and there's also the particular paper is part of that category of network security, network anonymity privacy, in particular the web-based timing attacks, leaking secrets over remote connections, and this is what I would like to focus on today in this talk. Before I get started with the details of this, though, let me, this talk is going to be a lot about time. So let me start with a philosophical quote on time. Time is free, but it is priceless, and that's very true. There are a number of further properties, like you can use it, but you can't own it. I change a bit the quotation here. You can spend it, but you can't keep it. And once you've lost it, you can never get back. So time, beyond these philosophical questions, has certainly a very special role in the security investigations that we do in the lab. So time has a number of matters crucially. So it has a crucial importance for security, for achieving security, but also for attacking systems. And so this combination of time and security, let me just give you a glimpse of what that means for the 3 areas that I started to talk about at the beginning, what my lab is actually working on. So when we look at these 3 areas that I just introduced, for the first area on LTE security, we recently had this paper, Call Me Maybe, eavesdropping encrypted voice over LTE calls with an attack called Revolta. There, it's actually the clicking doesn't work anymore. What's happening? Now it comes. Okay. We actually conducted an attack where the attacker had to be pretty fast in mounting it, in the sense that a second call had to be initiated in a fast manner with an initial target call. And if this was done fast enough, then there's actually the key stream. We could demonstrate the key stream is actually reused. And if that was done fast enough with the second call, the attacker could actually, since it's a stream cipher, so XOR operations, if that's done fast enough, the attacker could actually infer information on an encrypted voice over LTE call. So the core of this is not necessarily time, but here time matters. Time mattered a lot for the attack to be possible. One example for where time mattered. A second example. Okay. Second example is our investigations of GPS spoofing, and here for all kinds of localization of satellite-based navigation system, time is a crucial component. It is basically the 4th component for localization. So we have 3 X or Y, X, Y, Z coordinates as 3 dimensions for localization. And for all satellite-based navigation system, time is the fourth dimension in that, and it's crucial for being able to localize yourself with GPS. You would also need to time synchronize, so these are really intertwined with each other, and there's no way of taking them separate. So time has an immense importance there for localization and for secure localization in particular. And as the third example, on network and network security, there's the resistance to timing attacks, where actually time is of crucial importance. It's a central aspect of the security. When we consider side channel attacks, timing attacks in particular, it's all about time there. And this is what I will focus on in the rest of my talk. Okay, so much about the general introduction on the research that we do. Now, I would like to talk about timing side channels. So what are timing side channels? The concept is fairly simple. If there is a dependency on data that is supposed to be secret, and the execution of a program depends on the secret, then if there are different execution paths, or the length of the execution paths are different depending on that confidential or secret information, then there's a risk of the timing side channel, because if that secret is a certain value, then the longer operation in that example might be executed as opposed to a shorter operation that would be executed in a different case. So we get this dependency of the length that it takes for a program to execute based on certain secret input. And if a program shows this behavior, basically then the system may be subject to timing attacks that can then disclose information leaks about the secret, often not directly revealing the secret itself, but allowing an attacker to learn about the secret. This is something that I interestingly started working on about 15 years ago in my master's thesis when I was finishing my my undergraduate degree. And I have not much worked on that since. We actually started working on that again, also on time chaining attacks when Tom van Guttem actually joined my lab for a certain amount of time. So it was a nice closing cycle to where I started off many years ago. Let me give you a further example what that means. So the slide before was just about the concept of timing side channels, timing attacks, or the timing side channels. Now, how can that actually reveal something about the secret? Let me clarify that with a further example here. When we look at the operation of string copy or string comparison, string compare, we would have two words here, compare if they are the same. What would happen, the program would go through sequentially and compare the individual letters in these words. And we would start with the first two letters, make a comparison, are they the same? And if that's the case, then it would basically continue, go to the next, so continue with the operation and compare the next two letters. Again, do a comparison. There's an execution of the operation again. And this goes on for the next letters here. They are always the same for the first four letters in this specific example. And then we hit the case where the two letters are actually not the same. So here we observe that they are not the same. And then, well, if it's a string comparison, it would return, so they are not the same. These two words that we compare there are not the same, and the program would return and exit. Now, when we look at each of those operations, they will have a certain running time. If we compare individual letters, then it's likely to be a specific fixed running time. But we can see, depending on how long, so how much similarity there was between those two words, then this operation will take longer the more the words were the same. So here the first four letters were the same, so it would take around 500 nanoseconds for that program in that example to actually return. And then one can learn something about the password, if it's similar to some of the other words, or until which letter it is similar, until which letter it's similar to the word. And gradually one could actually reveal the entire password in this manner. Okay. This all depends on these execution times to be measured precisely. And this is something that we will focus on. So when we look back or look at the evolution of timing side channels, in timing side channels on crypto systems all started back in 1995, where Paul Kocher actually performed first cryptographic attacks, side channel attacks on RSA, was later followed by attacks on other cryptographic algorithms on ciphers and product ciphers in 2000. On AES, their cache timing based attacks were introduced by Bernstein in 2005. And what we've seen also recently, what got a lot of attention are the meltdown and spectre attacks that are not directly attacks on ciphers, but on CPUs. But what we have in common here is that it's attacks on specific, on systems, on embedded systems, on computers. So this is what these attacks share, and they all use timing information. In the last example for a meltdown and spectre attacks for opportunistic execution, for certain predictions of the program, using these timing side channels to make predictions and learn about parts of the memory that one should not get information about. So this is the part where the attack is directly run like on the cipher or on the CPU. What else is there? This is timing attacks executed over networks. So we can think about the example that we have here. The attacker is actually trying to run a timing attack on the server, and that server is remote. So it would not directly have it at hand to execute the timing attacks and measure timings, but would have to go over a network, send packets, wait for return packets to actually measure timing behaviors of the server. This is also a line of research that has started almost 20 years ago with timing attacks on web privacy. And then there were demonstrations of remote timing attacks in OpenSSL. So basically the cipher attacks that I've shown in the slide before, like on RSA or on AES, that they could actually be executed over a network. So you would not need to have the device directly at hand, but executing it over the network is something that is feasible. This requires a lot of network measurements. More attacks in that direction have come up. The last prominent ones, Lucky 13 with attacks on TLS, timing attacks on TLS. This is all on the network. So over networks called remote timing attacks or network-based timing attacks. What can be done with those attacks? Well, on the one side, on one hand, we can do the same as with the attacks on the Ciphers directly. They can be used to extract private keys from web servers, but they can also be used to extract all kind of other confidential information. Some examples listed in on that slide here. So for example, test if a username has a certain validity on a secured website, or will reveal, for example, number of private photos that exist in a publicly viewable gallery where the photos cannot be seen, but one can predict how many private photos are there. These are some examples of what types of confidential information can be detected by a network-based timing attack. And here I also mentioned cross-site timing attacks that were originally developed in 2017 by Bortz and Monet, where actually the server would or the server would learn if the user is logged in somewhere else. So basically the attacker would not have to attack the server right away, but there would be an intermediate step where the attacker is actually interacting with the user, and then with the server, and the attacker would learn if the user is actually logged in at a server. So it's not a direct attack, but in a certain form, an indirect or cross-site attack. I'll come back to that. Okay. Now, just for the concept, how do these remote timing attacks work? The concept is as follows. We have the confidential operations. The computations are run on the server, and the attacker sends off network packets that go in a maybe unpredicted path over the network. The response is calculated by the server, and then the response is returned. And what the attacker does is it measures the timings. So in that example here, there's a certain timestamp. So it's the round trip time that is measured from this operation, and it's just being reported. Now, doing that once is not sufficient, but we need a lot of those measurements. So in reality, the timings on the execution time on the server would be short, would be hundreds of milliseconds, or hundreds of nanoseconds, or maybe a few milliseconds. While the operations, while sending the packet over the network is something that takes longer. There may be congestion, maybe path loss, there may be longer paths that are taken. So that's the part that is actually a bit unpredictable. So the round trip times that are measured here are way beyond the execution time on the server. Okay. So how can we deduce any information about what's happening on the server in this case? We'll have to deal with that noise that comes from the measurements. And the way how this is done, so all the operations, so from the server to from the attacker to the server, and then back from the server to the attacker, there are a lot of small operations that have to be done that are all affected by jitter, congestion, delays. How we deal with that is that a lot of independent measurements must be taken. So you would record a lot of those measurements and then use statistical methods to infer the processing time of the request. Okay. And in many cases, the network path is the biggest source of jitter. That's the general case. Now, this brings me to just giving you a couple of results that we did for our paper, actually, to give you an idea about how many of those measurements need to be done. What you see here on the slide is the average number of requests that were needed in order to determine, so to run the attack, basically, for different timing difference. So here you see the timing differences of the execution time on the server. And what you see here is basically distances so that were sent over the network. So we used a server at a university in Central Europe and contacted other servers in the EU, in the US, and in Asia. And what you see here is the number of time measurements that had to be taken for having a 95% accuracy on determining the timing differences of those packets. So the longer the distances were, so in this direction here on the x-axis, the more measurements are actually required to receive reliable measurements. And also, obviously, the more, so the smaller the timing differences are on the server side for executing the commands, the more network measurements we'll need. And where you see empty fields here, this is basically where an imposed maximum from us of 100,000 requests had to be exceeded, and then we just stopped the attack. Okay, so this was a lot of introduction. Now let me come to the actual contribution that we did on that. And we did something we call timeless timing attacks, or exploiting concurrency to leak secrets over remote connections. And so this work, as I mentioned before, was mainly done by Tom van Goethem and Matti Vanhoff. And I also would like to give them credit for a substantial part of these slides that I'm showing here. And what is the core concept of that? So the core concept is we talk about timeless timing attacks. So what is timeless about those timing attacks? So we do timing attacks, but we don't actually use absolute timings. The idea is as follows. The absolute response time that you've seen on the example before is actually unreliable because of this jitter on the network. So we would like to get use of this notion of time. And how do we do that? The idea is to, instead of relying on these sequential timing measurements of this large number of timing measurements, we introduce concurrency in the way how the packets are sent out. So we are sending the packets, always pairs of packets, two packets together, and then only consider the response order. So those two packets are sent, they return, and we consider the order in which they come back. So in the end, we don't take time measurements, but we take just measurements of the order in which the responses are received after these packets have been used and processed by the server. And in this way, they are to a large extent, so these timeless timing attacks are to a large extent agnostic to network jitter, or to a large extent unaffected by network jitter. And I'll give you an example first before explaining that. So in the attack, what we would do is, instead of sending, so we would not take time measurements, so we can throw away the time here, but instead of sending a lot of individual packets individually, we send pairs of packets that go through the network now, reach the server. The server processes these two requests that were received simultaneously, will produce the responses, but one will be a bit faster executed than the other. And there's one that comes first, and this will be returned. Oh, sorry, I clicked too fast. And this returns, so those packets take the return path as well. And we just take note of the order. So which packet was received first over the other. So let's say in this case, packet A that was sent out was received before packet B. We also have to do a number of measurements. We cannot do with one only, but we do it again. It may give us the same order to a high percentage if a lot depends on the timing on the server actually only, but we may also have some instances where actually the timing is reversed. But in the majority of cases, the timings will be the same if the execution time on the server is such that task A is executed faster than task B. Now let me reason about why this is actually the case. And so let me present the model of what's behind this attack. What you see here is the calculation of the response time or the round trip time in general. So what does the round trip time depend on? Well, it depends on the processing time on the server, which we call small t here. It also depends on the propagation time B, so how long it takes for the packets to go through the network to be propagated in uplink and downlink direction. And it depends on the jitter, so the uncertainties, the variations, and on the path of the packet. Now we have a little subscript here, M, that actually indicates the individual processing tasks. And what we see in this formula here is that the propagation time itself does not depend on the processing task. So when we have a task and we send it over the network, the propagation time for that will not depend on what the task actually is. And also on the way back, we take the time measurements. So in the end, we will just take orders of packets, but the original idea with time measurements is that we would just take the original timestamp when the first bits of the packet arrive, so it doesn't matter how long the response actually is. That's why our B here does not have a subscript M. Now, this jitter concerns all the individual sub-operations that have to be done while the packet is propagated through the network. And we can then basically be reformulated by summing up over all the sub-operations that have to be done. So we look together at the propagation time and the jitter per subtask, per sub-operation. They are all summed up and then added to the processing time on the server, and all of that together will be our round trip measurement response time. Now, when we send not only one packet here, but a pair of packets, what we get is actually we can focus on the order at the end. When is actually our round trip time for packet X larger than a round trip time for the packet Y? And this is the case when, well, we just plug in these two formulas here. When this is the case, we take our processing time to the left side and take this part here to the right side. And what you end up is this lower part of the formula here. So this part of the formula, what does it tell us? It tells us that the order in which the packets arrive is determined by the jitter on the network. So we basically lost the dependency of the propagation time here, because the propagation time of the packets here, this VK, will cancel out. And this is the core idea, namely that the order of the response times leaks the order of the processing times on the server, under the condition that the difference is higher, so that the difference of the processing times on the server is higher than the combined jitter of both requests. We further reduce the jitter. So the idea is really to reduce the jitter here. We do that by having combined the requests in the one packet, at least for the uplink direction. There, they will actually experience exactly the same jitter. So their difference will be 0, which is exactly what we need here. So for that, we kind of reduce the jitter a lot. And this is the advantage that we get by focusing on the order of responses, as opposed to the traditional way of measuring the full round trip time. And that's why we can, in the end, achieve similar accuracy with less measurement reports. Now, let me just make clear the requirements that are needed. There are 3 requirements for that to work. First of all, the requests need to arrive at the same time at the server. I'll come into a second how we achieve that. The server second needs to process these requests concurrently. I will come to that as well. And the third one is we need to, so basically the response order needs to reflect the difference in execution time. And this will be the case if the network jitter, so the sum that we had and at the end, the difference between the network jitters of those two return packets is actually less than the difference in execution time. So what do we do with these three requirements? The first one is the simultaneous arrival. So having packets arrive at the same time at the server. There are two options of achieving that. First one is to actually use multiplexing. That's a new option or a new way that was introduced with HTTPS 2, where requests are sent as headers frames, and one is actually allowed as opposed to HTTP version 1. One can put two frames in a single packet, and that's exactly what we need here. When two packets can be sent out in the same packet, then they will arrive at the same time at the server, and that's something that the attacker will control of here. A second option is when this is not given, in particular for HTTP1, where this is not supported, then these packets can be encapsulated we need something to encapsulate the packet. And one idea here is to actually use Tor, because multiple TCP connections can be encapsulated in one Tor cell, actually in two Tor cells that are then merged into a single TCP packet. I show that on this next slide here. So this is the idea of having just one simultaneous arrival, one HTTP2 packet. The other one is using actually these two packets of HTTP1 plus Tor together. We're able to make them fit together. We have two more requirements regarding concurrent execution, where typically that is something that is provided unless there are sequential crypto operations where this will not work. And the response order is something that that matters. Most operations will generate the response immediately, and then this is typically fulfilled. But that's something where actually defenses can actually have a starting point against these attacks. Now, let me make clear what are the different attack scenarios. So far, I've just mentioned direct timing attacks. We are also considering cross-timing side channels attacks, as well as Wi-Fi based authentication. I won't have time to go into the details here, but there are different ways of how this can be executed. When we look now at the results, and here I'm really focusing on the simplest case of the direct timing attacks from the attacker to the server, we would have here on the left-hand side the traditional classic timing attacks, and on the right-hand side here you see a part of the timeless timing attacks for the HTTP2 setting. And what we have here is that you see a considerable smaller number of packets that are actually required to have for getting the same accuracy in time measurements. This is the major result of this work. This is the major result that we can, just by focusing on the order of the arrival of packets, we can actually achieve something where we need to perform way less operations, and we are getting in a certain way agnostic to the network jitter on the way, and are still able to perform measurements of execution times on the server. Okay. I can say a number of things about defenses. There are different options. All of them have their, in a certain way, pros and cons. Constant time execution would be great, but that is not very easy to achieve for many applications. Random delays can be added. We may want to prevent like that multiple packets are sent in the same packets, but then there may be performance disadvantages. So this is basically what we are facing. But let me come to the key takeaway, to the conclusion of that for this presentation here. What we have proposed is something that gives us a 100-fold actually improvement over classical remote timing attacks, because we could measure and for timing differences on the server as small as about 100 nanoseconds, as opposed to what we could measure with classical attacks in the order of about 10 microseconds. And this was achieved with way less measurements than before. And thus, these timeless timing attacks outperform the sequential attacks over networks, and they do have a similar accuracy when they are done on a local system. So on a local system, we don't gain much by doing them, but over a network, we gain considerably. We have executed that on a number of examples. We've used HTTP2, ARP password, and also Tor. And what's left to be done is understanding better if there are more protocols vulnerable to this attack, as well as working on the protection and countermeasure side. Thank you for your attention. I think this was about the slot that I had. I'll be happy to talk more about in the breakout session.